The James Webb Space Telescope, launched on December 25, will soon arrive at its destination L2 orbit. But it is not the first satellite to be there. ESA's Herschel and Planck have been there since 2009. NASA's own satellite was there from 2001 to 2010. What is so special about L2 orbit or even any Lagrange point? We will discuss this in this video. L2 may appear a futuristic and mysterious term, but its name actually honors a mathematician born in 1736. Lagrange points were named after Joseph Louis Lagrange, an Italian mathematician, and astronomer who made significant contributions to classical and celestial mechanics. Lagrange studied the three-body problem where three bodies are orbiting each other. In the three-body problem, you have two bodies that are very massive compared to the third one. The massive bodies can be, for example, Sun and Earth. And the third body is an object with a much lower mass like satellites or the Moon. While studying the three-body problem, Lagrange found that there can be 5 stable points in the space, in which you could put the third object with lower mass and have it stay fixed in place relative to the other two. These 5 stable points are called L1, L2, L3, L4, and L5. Normally, when you have two massive bodies like Sun and Earth, you will get an unbalanced gravitational force at a point in space. This will alter the orbit of whatever is at that point. But in Lagrange point, the gravitational pull of the two large masses precisely equals the centripetal force required for small objects like a satellite to move with them. This makes Lagrange points an excellent choice to put satellites, as they can stay in a fixed position relative to the Sun and Earth. At this point, it requires a minimal amount of energy as it needs few orbit corrections to maintain the desired orbit. Lagrange points L1, L2 and L3 are all in the same line with each other, while L4 and L5 are the points of equilateral triangles. The first Lagrange point L1 is 1.5 million kilometers from Earth towards the Sun. This point is ideal for solar observations, and there have been many solar observatories located here, including SCOVA, WIND, SOHO, and ACE. Lagrange point L2 is on the other side, with the same distance of 1.5 million kilometers away from Earth. There are other satellites in L2, including WMAP, Herschel, and Planck. While all Lagrange points are gravitational balance points, not all are completely stable. L1, L2 and L3 are not stable. They are like a point on the top of the hill. So any slight movement will make it go away from that point. Because they are not stable, they require the thruster to maintain an orbit at that point. But L4 and L5 are stable like on the bottom of a bowl. This also means that this point collects other objects like asteroids. Because of this, Jupiter has more than 1 million of Trojan asteroids at its Lagrange point L4 and L5. So why do we send Webb to orbit at L2? L1 is closer to the Sun. Since Webb requires a cold environment, it will be difficult to maintain it here. L3 is not realistic as it is much further. L4 and L5 collect asteroids, so it is dangerous to put a satellite there. This makes L2 an ideal location for infrared observation, and this is the main reason why Webb should be at the L2 point. Webb primarily observes infrared light. This can feel something like heat. Webb will be observing the very faint infrared signals from very distant objects, so the telescope should be shielded from any bright hot sources including the satellite itself. Webb will therefore require a sun shield to separate its telescope instruments like a sensitive mirror from the Sun, Earth, Moon and the spacecraft bus itself. Otherwise, the data will be completely corrupted. The telescope itself will be operating at about 225 degrees below 0 Celsius. The temperature difference between the hot and cold sides of the telescope is huge. You could almost boil water on the hot side, and freeze nitrogen on the cold side. To have the sunshield be effective protection against the light and heat of the Sun, Earth and Moon, these bodies all have to be located in the same direction. At L2 orbit, the Sun, Earth and Moon are always on one side of space. This allows Webb to keep its telescope optics and instruments perpetually shaded, enabling it to get cold for infrared sensitivity. Yet, Webb will still access nearly half the sky at any given moment for observations. To view every point in the sky over, it just needs to wait few months to travel farther around, which reveals more of the sky, previously behind the Sun. With the Sun and the Earth in the same part of the sky, the Webb telescope will enjoy an open, unimpeded view of the universe. In comparison, the Hubble Space Telescope is in low Earth orbit where it goes in and out of the Earth's shadow every 90 minutes. Hubble's view is blocked by the Earth for part of each orbit, limiting where the telescope can look at any given time. Webb will not sit stationary at L2. Instead, it will be orbiting around it. It is simpler, easier, and more efficient to orbit around L2 than to dwell precisely at that point. In fact, Webb's orbit around L2 is larger in size than the Moon's orbit around Earth. Furthermore, by orbiting rather than sitting still at L2, Webb will also never have the Sun eclipsed by Earth. This is necessary to maintain Webb's thermal stability and for power generation. As we mentioned before, this Lagrange point L2 is not completely stable. Because of this, Webb will have to make occasional minor adjustments to maintain its orbit around L2. The spacecraft is designed to carry enough propellant to make these adjustments for at least 10 years. However, NASA reports that a smoother journey of Webb so far leaves it with additional fuel extending its lifespan in space. The position of Webb at L2 also makes it easy for us to talk to it. Since it will always be at the same location relative to Earth, we can have continuous communications with it. Since Earth rotates, using 3 large antennas on the ground located in Australia, Spain and California, continuous communication continues. During routine operations, Webb will uplink command sequences and downlink data up to twice per day, through the Deep Space Network. It took roughly 30 days for Webb to reach the start of its orbit at L2. Compare it to 3 days it takes to get far away as the Moon's orbit. Generally speaking, getting a spacecraft to L2 is fairly straightforward, but Webb's architecture has a twist as nicely explained by Karen Rickhahn, Webb's flight dynamics lead engineer. Think about throwing a ball straight up in the air, as hard as you can. It starts out very fast, but slows down as gravity pulls it back towards Earth, eventually stopping at its peak and then returning to the ground. Similar to your arm giving the ball energy to go up a few meters from the Earth's surface, the Ariane 5 rocket gave Webb energy to go the great distance of 1.1 million kilometers, but not quite enough energy to escape Earth's gravity. Just like the ball, Webb is slowing down and, if we allowed it, would eventually stop and fall back towards Earth. Utilizing thrust every 3 weeks or so from small rocket engines aboard, Webb will keep it orbiting L2, looping around it in a halo orbit once every 6 months. So, why did the Ariane not give Webb more energy and why did Webb need course correction? If the Ariane had given Webb even a little bit too much energy than needed to get it to L2, it would be going too fast when it got there and would overshoot its desired science orbit. Webb would have to do a significant braking maneuver by thrusting toward the Sun to slow down. Not only would that big burn cost a lot of propellant, it would be impossible because it would require Webb to turn 180 degrees in order to thrust toward the Sun, which would have exposed its telescope optics and instruments directly to the Sun, thus overheating their structures and literally melting the glue that holds them together. Mounting thrusters on the telescope as a way to direct braking thrust was infeasible for a number of reasons and was never a design option. Therefore, Webb requested just enough energy from the Ariane rocket to ensure that we would never have to do a retro burn, but would always require a burn from the observatory to precisely make up the difference and place it in the desired orbit. The Ariane 5 targeted Webb so accurately that our first and most critical burn was smaller than we had to plan and design for, leaving more fuel for an extended mission. Even before the Webb telescope, L2 has been known to astronomers as a good spot for space-based observatories. There are already several satellites in the L2 orbit, including the Wilkinson Microwave Anisotropy Probe, and the Herschel and Planck Space Observatories. But there's plenty of room for another neighbor, and the Webb telescope will be heading out to L2.